chemistry, we often analyze samples of materials to determine their properties and composition. These analyses may be quantitative or qualitative in nature. While quantitative analysis measures how much of a substance there is, qualitative analysis establishes what that substance is. This video outlines the techniques involved in elementary qualitative analysis and the chemistry that underpins it. On completion of the qualitative analysis, which involves identifying the constituents of single substances or mixtures, you should be able to 1. Identify the cations: lead 2+, aluminum 3+, calcium 2+, zinc 2+, iron 3+, iron 2+, ammonium, and copper 2+ ions. 2. You should also be able to identify the gases: hydrogen, oxygen, carbon dioxide, ammonia, sulfur dioxide, chlorine, nitrogen dioxide, and water. 3. And you should be able to identify the anions: carbonate, sulfate, sulfite, nitrate, bromide, iodide, and chloride. Since most methods of qualitative analysis deal with ions, it is useful to keep in mind some of the properties of ions. 1. Ions can form insoluble compounds with other ions. 2. Their color or lack of color in solution or solid state is a fairly accurate indicator of the nature of the substance. Based upon this, if the compound is black, it is probably an oxide. If the solid or its solution in water is colored, this indicates that a transition metal ion is probably present. Iron 2+ solutions tend to be green, copper 2+ solutions are blue, and iron 3+ solutions are yellow. If the compound appears as a white solid and its aqueous solution colorless, this indicates that the transition metal ions are probably absent, the notable exception being zinc, whose compounds are colorless in solution and white as solids. So you see, looks can be deceiving. Appearance is not a 100% effective guide in determining the identity of a compound. The general method involves identifying metallic ions or cations based on the color and solubility of the hydroxide formed when they react with aqueous ammonia and aqueous sodium hydroxide. If this does not narrow down the unknown to a single cation, a confirmatory test will need to be done. The general method of analysis involves, firstly, preparing a solution of the solid under investigation. Next, place a sample of the solution in a test tube. Then, using a dropper, add sodium hydroxide solution dropwise to see if a precipitate forms. The next step involves adding excess sodium hydroxide solution to see if the precipitate dissolves. If no precipitate forms, warm gently and test for ammonia. To another portion of the solution, add aqueous ammonia drop by drop and look for precipitate. Again, add aqueous ammonia in excess to see if the precipitate dissolves. If required, carry out a confirmatory test on another portion of the solution. The metal cations form insoluble hydroxides with sodium hydroxide solution. The precipitates formed are colored as follows: copper 2 hydroxide, blue; iron 2 hydroxide, dirty green; iron 3 hydroxide, reddish brown. All other precipitates appear white. Calcium hydroxide, copper hydroxide, iron 2 and iron 3 hydroxide are basic and therefore do not react with excess sodium hydroxide. Precipitates remain. Aluminum hydroxide, zinc hydroxide, and lead 2 hydroxide are amphoteric. They react with acids and bases. They react with excess sodium hydroxide to form soluble salts, hence the precipitates appear to dissolve in excess sodium hydroxide. The metal hydroxides formed with aqueous ammonia are insoluble in excess except copper and zinc hydroxides, which dissolve in excess aqueous ammonia as soluble complex ions are formed. Aqueous ammonia will not precipitate calcium ions. Calcium hydroxide only precipitates when the concentration of hydroxide ions in solution is relatively high. As ammonia is a weak alkali, it has a relatively small amount of hydroxide ions in solution when compared to strong alkalis. The zinc ion is generally confirmed by the fact that its hydroxide is soluble in both excess aqueous ammonia and aqueous sodium hydroxide. To differentiate between aluminum 3+ and lead 2+ ions, solutions of iodide, chloride, or sulfate can be added. In all cases, lead 2 ions will form a precipitate while the aluminum ion will not. These precipitates are lead 2 chloride, white, lead iodide, yellow, and lead sulfate, white. The amphoteric hydroxides, aluminum hydroxide and lead hydroxides, and the basic hydroxides, iron 2 hydroxide and iron 3 hydroxide, do not react with excess ammonia solution. The precipitates remain. Zinc hydroxide and copper hydroxide react with excess ammonia solution, forming a colorless and a blue solution respectively. Precipitates disappear. The ammonium cation does not form an insoluble hydroxide, but on heating reacts with the hydroxide ion, forming ammonia and water. Ammonia gas turns damp red litmus blue as it is alkaline in nature. It also has a pungent odor and forms dense white fumes with hydrogen chloride gas. The conformation of the ammonia gas confirms the presence of the ammonium ion, NH4+.